send the device to, okay, we can send the device to the well site to have the work done basically in real time. The resolution can get up to 55 micrometers. Just for comparison, the medical CD, I guess most of you guys are familiar with medical CD to medical CD, most of the time the resolution is about kind of a 500 micrometer. So 10 times lower than what we are using. Okay. I was confused. Okay, I just give you some quick example what the 55 micrometer CT can do. Basically, get the picture of the focal and also got the information of fractures and have all the statistics about the length of the opening and also the and also we use the fractures to calculate fracture permeability porosity. So just very quick. This is a more detailed picture. We were able to get, this is one of the kind of 2D section. This is a kind of animation of how the fracture looks like. I just gave you two examples. This is the fracture created by fracking. So hydraulic fracking. And we all, okay, hang on. Sorry for the, I'm not really familiar with this. Okay, what you can see, all these tiny fractures, we'll be able to identify and describe all those tiny fractures. Some of them are created by fracking, but some of them just kind of the feature of the rock. And some other things we can see if there was any kind of proppants or kind of mud residuals sit in the fractures. We're able to run out of battery. No. Okay, can I have another pointer? No, the pointer. Yeah. Okay. Yeah, okay. I'll just continue. Again, this is might not be the kind of area you guys are interested in. I just show very quickly what the company can do, just in case you guys need it in the future. We can talk more in details. Oh, it could be they just run out of battery for the whole remote control because. Okay. Then cycle core or core plugs. This is our kind of we got our reputation for work with CNOOC in South China Sea. Okay, so this is what we call portable CT. We call CTDLC 1000. The size is about kind of 70 centimeters long. This was probably the first, globally, the first portable CT can working on offshore platform because it can handle the noise, can handle the vibration. So the device will be able to produce very high quality data even in a very harsh environment, which is critical. And the, okay, yeah. So the principle of the CT, I guess most of you guys just shoot X-ray through the rock. Then different mineral will have different, which was kind of a absorption kind of capability, energy. Basically, when the X-ray shoot through mineral, the X-ray will be absorbed by by minerals. So what the X-ray can pass through kind of have relationship depends on the density and also basically the mainly density of the mineral. Okay. Okay, thank you, Aston. So correct. And what the resolution of this device can up to 0.5 micrometer, which is 500 nanometers. Okay. Okay. These are another devices, XRD, XIF, which most of you guys are very familiar with, and also SEM, scanning electric microscope. We use this devices together with micro CT to get a kind of a more full spectrum understanding of the rocks. Okay. Oh, thank you very much. Okay. Well, this is the process, which I'm not going to go through in details. Basically, you talk sidewall or cuttings in this example to kind of three major steps that I would like to describe. You get, so how the CT scanning work is shoot multiple, up to 1,000 kind of 2D section of the rock, then combine all the kind of hundreds or thousands of 2D image in together to make a kind of 3D, kind of reconstruct the rock into a 3D model. Okay, so then so this is what it look like. After we scanning of the rock, then combine the hundreds and the thousands of the 2D images into a 3D model. Then we do several things. One is to measure the pores and the pore throws in the 3D model and to calculate the porosity and also calculate the kind of pore distribution, which is not just the porosity, basically a very detailed distribution of different size of pores. How many big pores, what percentage of big pores you have, what percentage of small pores you have, which is critical. I'm going to kind of talk a little bit more in detail. So, yeah. Can do both on sidewall core and the cuttings. Right.
Yeah, but for us, it can directly generate core analysis based on. I think it's very rare if
Right.
oil and gas right now. The technology only coming from the core.
Right.
If you try to analyze the core based on cuttings, so we have to remove all these OBM, oil-based part, water-based part, or how we can distinguish between the big rock bit analysis. I mean, once your bit is crushed and formation, it creates crack itself.
Right.
So it would be affected by erosion itself.
Right.
And how can be distinguished between the porosity coming from the formation itself between that?
This is a great question. So because it's so critical. The answer is yes. Okay, several things. First of all, we don't need to, well, there is a catch. Basically, the cuttings need to be good enough. Otherwise, the cuttings, it will not be able to represent the rock, right? If the cuttings is too small, so then it's useless because it's only kind of the several grains. Then also the fractures and also the grains between grains will be loosened, right? So we do need to select very carefully about the good cuttings so that it still kind of present like a rock. So I will give you some examples, see if that's kind of good enough, if the results from the cuttings can represent the rock. Second thing you mentioned is because the cuttings will somehow be contaminated by mud, oil-based mud or water-based mud. For our process, we don't need to wash or dry the cuttings because the fluid, different type of fluid, have no effect to CT technology. Okay, so the contamination or the mud will have no impact to our technology. But your question, the most critical part, if the cuttings can represent the rock, right? That's a very critical. We did find it for some cases, because nowadays the big is so good that crash the rock into powders. For those kind of cuttings, no, we cannot apply our technology. So we found, as long as, but for if it's a very coarse rock, so what you mean, the grain size is bigger, so then 1 to 2 meter size of cuttings will not be good enough. Then the results using our technology will not be reliable. So, but we did find for the tight reservoir, for the fine grain rock, as long as the cuttings is 1 to 2 millimeter big, most of the time the results is reliable. I will show you some picture, show you some example, because that's a very critical question. So you can always kind of use your technology, give me the results. But if the cuttings is not the same as it is in the surface condition, right? So that's the critical. And also we did find sometimes the fractures caused, we call it kind of artificial fractures. So then we were able to, most of the time, we can identify if it's a kind of natural fractures or artificial fractures, but not all the time. So by no means there was no technology to our, no challenge to our technology, but this is the most critical question. Thank you for asking that. So let me go through. So we'll probably come back, see if I can gradually answer your question or kind of understand your concern, right? Again, if the rock is good enough, we'll be able to, both for sidewalk and the cuttings, to kind of reconstruct into a 3D model. I mentioned we can calculate or describe the pores and to do kind of pore do kind of pore distribution or pore structure distribute calculation. Another two things we can do, we can use the 3D reconstruct a 3D model to do things. One is to calculate permeability. The third thing is pretty critical for the wells, which need to be fracked to simulate the geomechanical properties, like Young's module and the Poisson ratio, which is very critical for the completion design. Yep. Okay, please.
Sorry for interrupt. As I mentioned in your resume that you've been work also for Eagle Ford formation. Is it shale formation? And in the like a Mesozoicum, yes. And I'm wondering, this is what kind of cuttings? Is it shale or sand? Okay. Because I cannot.
What kind of cutting?
Yeah, I cannot read the mineral identifications tables.
Yeah. So I would say most of our kind of project we have been working on for good reservoir, they don't need us, because for good reservoir, most of the time the conventional log will be able to answer most of the questions. So two major reservoir we have been working on. One is tight reservoir. Okay. Second one is the shale. Because those are the two type of reservoir, people feel like it's challenging to get a good understanding of porosity and the permeability.
The machine that you show us before, the machine, like the CT scan machine.
Right.
CT scan for core and cuttings.
And also for sidewall core, for the portable CT, because the sample is small, we talk core plug or sidewall core to use the portable CT to do CT scan. And also we do that. We follow the similar process for cuttings. Again, just kind of response to the chairman's question, the cuttings, we do need to pick up very carefully to get the good cuttings. And also the cuttings can represent the formation, which is always a challenge. Yes, yeah. Oh, yeah. Yes, we do. Yes, we did. I'm not sure if I can, but I do have a slides. But if I don't cover in my presentation, I sure can find the slides. I do have one example. We did the same analysis to sidewall core and the cuttings. Yes. Right. I do have one example. Yeah. Yeah. I mean, again, if you don't see it in this presentation, I should be able to find that for you. Okay. Well, again, I'm so happy. So this is all about my talk. So you guys, something you guys are interested in. Also have questions. Well, another question people ask, because for CT scan or any technology, when you enhance the resolution, what you mean, each time your analytical area will be smaller. So if I have this side of sample, if I do kind of for a smaller area, more high resolution analysis, I have to pick up some area because I cannot really do, it will take too much time. So then the question is, IO analysis can represent the whole rock. It's always a challenge. So what we try to do is to choose, first of all, you look at the whole image of the sample, then do scanning for the whole image, whole area. Then see, well, then you have to select several areas to increase your resolution. So the key thing is to hopefully the area you select can represent the whole rock. Because there was no 100% kind of a perfect solution, but you do your best. Hopefully the area you select can somehow represent the whole piece, whole rock. What we did before, so we use this, then jump to, you would do this 800 micrometer resolution to 220 micrometer resolution. Then we found we kind of jump too far. So then the result is not good enough. Then we do one more layer to add a 200 micrometer. So that you do this whole picture, then select several area, do on this kind of resolution. Then do the same process, select the same several area. Most of the time, the good area, or bad area, or mediocre area. So then you kind of follow the process again. You do this step by step. Hopefully, the result, we combine the results for all three levels of resolution, get a good representation of your sample. Does that make sense?
Compared to all rocks, I mean the different angles out.
Right. Yeah.
The cuttings, different resolution to create more colors, create more what kind of
I know what you mean. Again, this is a great question. Also, the very challenging question. To be honest with you, for geological analysis, you do your best. There is no perfect solution. So you do your best to hopefully get an 80% and 90% understanding, right? So for even for the kind of depth selection. So because for our kind of discrete type of analysis, your analysis to each points, then the question is, do this 3 or 5 or 10 samples can represent the whole interval? So this is where Mr. Jiang's technology may come to play. So each technology, no matter how good it is, can only solve part of the problem. So how can we make sure our kind of analytical point is representative? We'll have to kind of cooperate with other technology, like wireline logging, right? So you do kind of integration between the two technology to get understanding for the whole interval. Because no matter how good our technology is, we only apply analysis to several points. Then the question to your to yours is, okay, can this several points represent the whole interval? So we need to understand the whole the feature of the whole interval. So we had a great discussion in the morning during the breakfast time, how the two technology can work together. Because, you know, well, the advantage of wireline logging got a full picture of the reservoir. The disadvantage is, well, for the tight reservoir, it's very difficult for conventional logging to understand the permeability or the relationship between the porosity and the permeability, which is kind of key. I'm going to cover more. I don't know if, well, to be honest with you, there was no 100% perfect answer to your question, but you do your best. But that's, which is very key.
We deal with the different characteristics, for example, we deal with the different bases of sedimentology in the area. And then we try to combine the guidance and with the load. For some reason, for sometimes it will be
it's very difficult.
Confusing.
Yeah.
So what we have for the latest one is a load. So now we try to digging more about the guidance, still struggling with that.
Yeah.
So that's really interesting for us. When your technology comes to us, and then.
But to be honest, well, Lily just mentioned to you. So that is so for each sample we pick up not just the one cuttings, one sample. We select multiple samples. Hopefully get a kind of a. I would say it's 100% is a perfect solution. What you try to do is can I get 80% and 90% kind of representation of the of the information. To be honest with you, even I just this is probably a little bit over our talk today. Even between our technology and Mr. John's technology, we are still having gaps in between. To be honest with you, because you guys are all kind of experts, so it's not easy to correlate well data with cutting, right? So there was still something we need to working on to fill the gap to get a good enough understanding of your reservoir. So we're not done yet. I mean, seriously, this is one of the things we talked during the breakfast time. For conventional logs and cuttings, if you want to kind of try to create kind of relationships between these two, there's something missing in between. I just share very quickly is a very good understanding of the lithology, which we have been working on something to fill that gap. So again, this, I mean, it's good or bad. So after this meeting or presentation, we probably kind of found more challenge or more questions, which is good, which means something we can working on. I mean, the oil and gas industry has been kind of more than 100 years ago. We have achieved so much, but it was still there's still something we don't understand it very well. Okay. Again, thanks for your question. Right.
Until the CT scanning electron microscope or the other stuff,
Right.
We need to have a good preparation until the end of the game.
Right. Yeah.
We need to have fun together.
And also, I mean, today is just the beginning of our conversation. So there will, I believe, if you guys are interested, then we can work together. See, the major objective is how much we can help you to answer your question. So then again, let's try to work together, see what we can do. Okay.
They AI, random forest, neural network, blah blah blah, and we come up with the 70% is a match.
Right.
Different lay, different field here, different water basement, oil basement, different river apply.
Right.
Generate different analysis.
Yeah. That's a very good point. I mean, there was AI. I do believe AI will play a very critical role in our kind of area. So, well, let me try to. I will just go very quickly. So if you guys find anything, I like the way you guys are kind of asking, just whatever you guys just your concerns or questions. Let's talk about or that. Well, this is a comparison between with all kind of you compare your results. This is one of the questions people ask also. Well, how about did you compare the results by your technology with another more kind of conventional or industrially accepted technology? Of course, we did that because this is basically the permeability and the kind of the relation porosity between our technology and another conventional depth technology and this permeability. I'm not going to go to the details, but basically this is all the new technology. You will have to prove yourself. Is your results reliable? This is I just want to show one thing over here. So for the challenge to understand the permeability, most of the time we have been doing pretty good job to understand the porosity. But the challenge is if you just look at one area, let's see the 10% porosity, the permeability varies by 3 or 4 orders of magnitude. What you mean 10% porosity is good, but the permeability have a very wide range. So this is what we use, where you use the similar data. This is a kind of key finding or discovery of our technology. We found the big pore, we call micron pores, have much stronger relationship with permeability. Okay, so unfortunately, I do have one slide over here. Basically, if you look at the distribution of pores, the conclusion is the more big pores you have, the better permeability you will have, which makes sense. Let me just go through the 3 major kind of, I think I have a slide, but I just go talk through all those 3 points. We found 3 key parameters which have stronger correlation with permeability. One is distribution of pores. Secondly, was connectivity of pores. Okay, if the pores are very well connected, the fluid will be able to flow more smoothly. The third one is pore throw radius. Basically, the little river to connect all those pores. If you have a wider or kind of bigger pore throw, the better permeability you will have. Okay. But why I'm talking about this? Let me just throw. I haven't covered this already, but basically the beauty of this CT scanning or kind of micron resolution CT scanning, we got image of 2D and a 3D image of all those pores. I just want to show one example how the pores look like. Then we do digitalization to statistics all those pores and also to describe the connectivity of the pores and also measure the pore throw radius. So that is why we'll be able to understand the pore structure or micropore structure from sidewall core and the cuttings to understand the permeability and to create a relationship between porosity and permeability. So this is just one example to show basically we kind of just on this is one of the examples is kind of the relationship with production between production with the permeability. Basically, this is this example show the average pore radius, basically the kind of population of big size pores. The more bigger pores you have, the kind of better permeability and also better production capacity you have. This is the conclusion. Again, this is one example. We show kind of several major features. For each sample, you have micron porosity, you have nano porosity, the big porosity, small porosity, then the connectivity and the pore through radius. We have all the parameters for every sample. So that is why we have a better understanding of the permeability or production capacity of the reservoir. This just shows some example of how we do the analysis. This show the kind of 3D image of the reconstruct sample, kind of 3D samples, and also we inject fluid into the sample, then we can visualize the movements of the fluid through our sample. So that's what we use it for calculating permeability. Again, I'm not going to go through all those details. This is another example of what we call microfluid visualization and quantitative characterization. Okay, I just added this slides this morning. When people try to categorize reservoir, we say, well, I'm type 1, type 2, type 3 reservoir. Okay, so what does type 1, type 2 reservoir mean? For every area. So this is one example. We kind of create or work together with South China Sea, with CNOC. So say, well, for my area, you give me the permeability, but what I really understand is the productivity or commerciality. So then we kind of work together to create 4 types of reservoir. So for type 1 reservoir, the best one is can produce commercially by vertical well, which means the reservoir is very good. So then in this area, okay, for my area, for this formation, 50 millimeter. So with this permeability, I can produce the well with vertical commercially, which means I can develop by vertical well. The second is vertical well is not going to be good enough. You have to drill deviated wells, but no fracking needed. So as long as you kind of enhance, kind of have a long section of reservoir, will get good enough kind of production rates. The third one is, well, it's a reservoir, you have oil in it, but you have to frack the well. Otherwise, you will not be able to develop it. The fourth one is uncommercial on the current technology. So that is why for each area, you cannot just tell me my type 1, type 2. For different area, type 1, type 2 could be different. So you will have to create a standard for each area, how good the reservoir is good enough for me to produce or development well by a vertical well. So this is I feel like it's very interesting. I would like to share this with you guys. You cannot just measure the permeability, call me type 1, type 2, because different people can have different definition for type 1 and type 2. So this will make our work more meaningful for a certain area. Okay, let's move to cuttings. Again, I showed this already. We kind of follow pretty much the similar process for cuttings. Let me just Joe, I don't know if I can. Well, this one's basically the 4 type of information we can produce from both sidewall and the cuttings. First is the mineral and the lithology. That's the foundation of all the follow-up information we created. You will have to understand what kind of rocks you have, because to understand that different kind of rocks may have different relationship between porosity and permeability. This is our foundation. So I'm not going to go through the details. So by through the cutting analysis, we'll be able to kind of define content of each mineral, then combine into lithology. Second part, for unconventional, for shale oil and gas, the critical part we call organic quality. So which is, I mean, no matter how good the rock is, if there was no hydrocarbon in it, you will not be able to produce it. So one of the key quality people use to measure shale oil and gas, what we call organic quality. Most of the time they use TOC or gas content, but whatever measure you have to tell you how much hydrocarbon you have in it, which is critical. Second part is reservoir quality. We kind of, when I talk with sidewall call, I talk a lot about reservoir quality. Basically, the reservoir quality before fracking, which is the kind of natural nature of the reservoir quality of a rock. Without fracking, how good in terms of the reservoir quality, how good this reservoir is. So then we use porosity, permeability, pore distribution to understand the quality of the reservoir. But for unconventional, this is still not good enough because the reservoir is too tight. You will not be able to commercially produce it. Then you move into the third or kind of last step to understand the mechanical property, which is Young's module, Poisson ratio, because basically how much you can improve the productivity or permeability by fracking the reservoir. So that's what kind of 4 area we evaluating to use those information to kind of for completion design. I mean, before we came over here, I had you guys, some of you guys will consider fracking, right? Well, consider fracking not because we like fracking, because without fracking you will not be able to develop it, right? So I can leave the slides to you guys after, you guys can, if you have time, can look at more details. And also in the future, if a certain area you guys interested in, we understand more, we can always arrange, I can come over here or do the online kind of a discussion, okay? So basically this one to show Young's module, Poisson ratio, and also have all the minerals. Then we use this information to calculate rock mechanical properties. So this is the results. We combine our results. Again, I'm not going to go through the details. Together with Mr. Jones, what they have been able to produce was well logs, because we will have to combine or kind of integrate our results together with another more continuous results or more kind of people more familiar with results. Well, just a little bit kind of basic, because some of them, this might be too basic for you guys. I covered already. We use organic quality, reservoir quality, and geomechanical quality, 3 quality. These 2 we call geological sweetness. Mechanical quality is more kind of mechanical sweetness. So you combine this 3 pieces of information to evaluate how good your unconventional reservoir is. Well, this that can use this is an example, but in terms of kind of principally, the Thai reservoir follow the similar process. you have to have hydrocarbon. Hopefully, you have natural porosity permeability. Then your kind of a room for improvements by fracking is good, so that you'll be able to enhance your productivity by fracking. Well, just two kind of definition I want to clarify. I think most of you guys probably understood this very well. One is called Britness, so how much the rock can be fracked. The reason I showed this example have a purpose. Most of the time, people are using mineral content to calculate brittleness. Okay, because brittleness is critical for fracking, right? Well, the catch is what type of mineral you have in the rock. It, of course, is critical, but that's just part of the information. I would say for the same type of mineral, you just add them together. They may have different type of brittleness, or the rock strength will be different. So by using the content of a mineral will give you a good enough results of brittleness, but not the ideal way. So that is why we use our model. I'll just give you two examples. One is the smaller the grain is for the same content of mineral, the kind of harder the rock will be because the grain size is smaller. The second one, I just give you some examples. The second one is more compact rock will have a much stronger kind of geomechanical nature. So that is why just use the content of the mineral is not good enough. So that is why we got the mineral, then combine them into rock, then to use simulation to get the geomechanical properties. Second, again, I'm not going to go through the detail. Just, I mean, this is pretty straightforward. For brittleness and the frackability is not the same thing. They have very strong relationship, but not identical. I will just give you an example. Glass is very brittle. Okay, granite is very brittle. But if you apply the same force, you can easily break the glass, but it will be very difficult to break the granite rock, because the granite rock have much bigger strength. Does that make sense? So that is why you calculate the brittleness. It can give you a very good information, but if you apply the same kind of a completion, kind of a hydraulic fracking, the engineering, you will not be able to break the stronger rock like granite. So that is why by calculating brittleness is good, but not good enough. You will have to kind of consider how strong the rock is. Okay. This is an example of eagle fur. So I mean, for the first several stage, we use one kind of. I'm not going to go to the details. Because we use a very kind of high fluid rates, it was able to frack the formation, which is very strong formation, under the reservoir. Then with the lower down, kind of reduce, lower down the fracking pressure, then you see the fracking area is much smaller. So then again, you can say, well, this is too big, this is too small. Then kind of optimize the kind of engineering parameters to get a kind of more reasonable kind of fracking results. I mean, this is maybe a little bit too much. I just could give you examples to try to clarify some misunderstanding of in the unconventional area. Timing wise, let me just go through. Covered this already. We use kind of 3 quality to kind of basically for horizontal, for vertical with the same thing. Use kind of organic quality, reservoir quality, mechanical quality. Then we divide the horizontal well into different stages. Then you apply the different completion operation parameter depends on the property of each interval. Okay. Let me just then I think I've done most of the work already. Let me try to finish up in 5 minutes, maybe. So then the third part I'm going to cover very briefly is some AI technologies. We discussed about the big data AI technology. One is the web or cloud-based digital core platform, because the challenge for the digital core CT scanning, the data sets it's huge. So you cannot just easily send the results to your to customers. So instead, we work together with our vendor to use kind of web or cloud-based platform to manage our data. This is South China Sea. Server, it's a good question. Well, have to be the customer because we don't own the data. We kind of manage the data for you guys. So we have to be in your server. Yeah. Right. Yeah. There was a way to kind of cover your confidentiality. That's a good question. But we have to, because we, as a service company, we only kind of do the work for you. So then whatever you want to feel safe, you want to put it in, it got to be in your area. So then this is just some example we can not just store and manage the data created from our technology. We can also kind of work with you guys to manage the data you acquired from another vendors or from another technology. This second one is well, this is a very hard, used to be a very hard topic, is what we call kind of smart drilling system. So long story short, this one basically just combine all the drilling parameters and also logging the wireline logging, mud logging information to basically help you to understand the downhole condition during drilling the well. Then basically two purposes of this. One is based on your understanding of the downhole condition and the formation, how you can better design your drilling parameter to drill the well more faster or more efficiently. The second one is to avoid risk. So that's why people use the kind of smart drilling to integrate all the information to, one, improve drill efficiency, the secondly, to avoid bad thing from happening, right? So the third one is, it's very easy to understand. We kind of create it's basically the automated log interpretation tool. One of the challenges for some area, especially for the older area, they have hundreds of older wells. They don't want to do the petrophysical analysis for each and every well. Instead, they want to have an automatic tool. You can process multiple wells together to create very quick results. Basically, petrophysical analysis tool.
Working on AI, all these things, working on AI concept.
Yes. Yeah.
Can you back to the previous slide, please? Cooperation.
Okay.
Thanks. Next slide.
The next or this one?
Next. Yeah, this one.
Oh.
This one is working based on police, right? Or there is a tool to install equipment on the surface.
Yeah, on the surface. On the surface.
No need additional person for analysis, just automatically from the equipment.
Yes.
So just not like what you call the managed price of drilling equipment. Some of our service company already developed this kind of equipment.
Yes.
So
yes.
drilling under balance.
On the balance, well, this is just one of the application of this technology to drill on the balance I mean, then you will have to look at the kind of a situation, how can you handle the unbalanced? But this is not specifically, but it can work in on to help to unbalanced drilling. But this is not specifically to design for basically you can apply it to all kind of situation. But we will have to look at the details how you can, yeah. I know unbalanced drilling is one of the challenges. This is why I have the slides I have again. Thank you very much. But I do want to show one example. Okay, after this, this is in South China Sea. I think for operations, I know you guys have in this room we have some operations people. For operations during drilling, especially in offshore drilling, there are some kind of real-time decision, which is kind of critical. Okay. I will just give you a couple of examples. One is for MDT. I heard someone mention for MDT, one of the challenges for that high reservoir, it's very difficult to get a high successful rate because the reservoir too tight, right? But you wish you have some people to help you to understand, I mean, together with wireline, okay, to help you understand, well, where do I believe the reservoir quality is better? I can have better chance to get good MDT test, right? This is one thing. Secondly, is when you consider do TST, do testing, you wish you can pick up the best interval. Okay, I will just give you one example of this. I just love this one. I'm not going to mention the name of the well, but this is South China Sea. They did 2 DST. This is Grand Paleo Barrel Hill. So they did 2 DST, one on this rock, the second on this interval. Okay. They got no luck. They only kind of recovered a kind of filtrate fluid from this interval. There was no hydrocarbon recovered. They got some hydrocarbon recovered on this interval. Just look at the depths of this sample. This is 4320, 4325. Okay. They got some hydrocarbon oil recovered. Then we did all the cutting analysis we have done for them. Then we did cutting analysis on this sample. The depth, you can look at the depths all kind of deeper than this one. Okay. Then I asked them, did you consider to move your DST interval a little bit lower? Because obviously the rock quality of this sample is much, much better than this one. The data they used to design their DST interval with wireline included FMI. They got some interpretation to understand the fracture distribution of the reservoir. So they thought this might be a good one. So they got they got oil recovered, but not very good. So that's my asking them. So they said, I wish I had this information so that I would love to move the DST interval a little bit lower, see what I can get. I just want to use this as an example, cutting analysis, because we can get the analysis done within 30 minutes. So I don't mean this will answer all your question, but at least a very critical data point can help you to make a better decision. But this is a great example. When I show this, I don't want to kind of, you know, for cutting data. I'm sorry. Yes, yeah. That's a good question. So that's I mean, this chairman answered a question already. So we'll have to look at very carefully. So for example, this fractures is pretty obvious that created during the process, right? But this one, we're pretty comfortable. Some of them are natural fractures. This is another example. This is even deeper. So if you look at the porosity of this one, this is granite. It's pretty obvious and it has a very good porosity and permeability. I'm sure you're absolutely right. We have to look at very careful which fractures are created by student operations, or even when you're handling the samples. It's not always easy. Sometimes we can tell the difference, but not all the time. I don't want to show how we are just too smart. No, it's difficult. Yeah. What I mentioned, I mean, I don't mean we will provide 100% of your just very critical data point. This is about geology. There was nobody is smart enough. Well, just listen to me. I will solve all the problem for you. No, nobody can do that.
So you have a specific personnel in the science.
Yes. So the experience is very critical. So even within our company, there was only 2 or 3 kind of very experienced engineer to kind of handily pick up the good sample from critical wells. It's so difficult. And again, I mentioned already, most of the times the cuttings are not good enough. So we have to kind of pick up very careful. Let me show if I think again, I remember your question, the comparison of the cuttings and sidewall core, and also I do have it in my computer, but I cannot show it. What I can do after the meeting, I can send you 2 examples. One is the comparison between sidewalk and the cuttings. Another one is to answer Chairman's your question. See, just look at the image of the CT. Do you feel comfortable the results from the cuttings is good enough? What is kind of 1 to 2 millimeter area image? We feel pretty comfortable. The grain size of the cuttings can represent pretty well of the rock. So that's a very critical, because so that is why I mentioned earlier. If for the coarse reservoir, it's more challenge, because for this size of cuttings, there are only several grains. So on the surface condition, it's quite different from it is on the subsurface condition. But for Thai reservoir, we are pretty confident. You feel like the results from the cuttings is good. Let me see.
See the oil contains below the UV. Some reasons you can see diagram, but after we compare with the water level. What I'm trying to mention you guys is here you're dealing with the multi-layer reservoir characterization.
Right.
We're dealing with the base oil, we're dealing with the water base. When we're dealing with the
You mean oil, water-based mud, oil-based mud, you mean? Right. Oil-based mud, okay.
Usually when we see the oil show based on guidance, we cannot see on the water level.
Okay.
Oil-based.
Right.
Distinguish between the oil-based one coming from OBM itself or coming from oil formation.
Right.
It's still difficult.
It's difficult, right?
So it's very interesting for us if you say you can directly, you have an example compare with the values and the logs and you create the same value of the porosity or the result. Very good.
Yeah, okay. So, I mean, the several things we have been trying. One is, of course, the comparison. I mean, that's the validation of your technology, comparing the results of your cuttings and your sidewall core. Well, just mentioned there's so many challenges for cutting analysis, to be honest with you. Even though I think we have achieved quite a lot, but still challenges. Another one is depth calibration. For operations people, everybody know, okay, you got the cuttings for certain depths. The question is that cutting from that depth? Right? So, well, you do your best to kind of do your calibration for depths, then still sometime, the cuttings came from anywhere in the wellbore, right? So that is why we pick up several points, several samples for each cuttings, and also use another data to kind of confirm, how much you can tell that cuttings is from that depths. It's not always. Well, the good thing about cuttings, so if you look at if you just look at one sample, then you compare with wireline, it's difficult. Well, the good thing about cuttings or the things you have so many of them, hundreds and thousands. So as long as I'm not recommending you just look at one or two data points. For all type of mud logging technology, including cutting analysis, you will have to look at the whole picture, right? So as long as you you look at 3 to 5 samples from each cutting bags, you got pretty confidence. The sample I got are from that depths. Again, you have to look at the big picture.
Excuse me, Mr. Dai, there is a question in Zoom chat from Mr. Giga Sakti. Good
Please.
afternoon, Mr. Dai.
Yep.
Thank you very much for your excellent explanation about digital rock technology. I would like to ask you two questions.
Right.
Number one, how digital rock technology resolve the limitation of representative volume sampling with different basin conditions? And the second question, can digital rock technology be a primary method, or should it just as a secondary approach to core analysis? Thank you, Mr. Dai.
I'm sorry, can you repeat your question again? I want to make sure I understood your question. So your first question is about, can you say it again?
Okay. The first question is, how digital rock technology resolve the limitations of representative volume sampling with different basin conditions?
Was different what condition?
Different basin conditions.
Oh, okay. Yeah. Let me just go one by one. For kind of two levels. For just direct results like the porosity or pore distribution, then you don't have to consider too much. You basically to kind of get the image, you kind of do statistics based on sample. Okay. But the second part of the second part of your first question is kind of is critical, is more region or basin kind of related. So that's, for example, when we use the data we acquired from the cuttings to do simulation to create, for example, geomechanical property, right? We'll have to consider the local condition to define your model to get the kind of more fit parameters to get the meaningful results for each certain area. So for direct measurement, doesn't really matter. You get what you see. But for anything need to use simulation, we'll have to use consider the similar local condition. Then we will have different model for different area. Did I answer your first question?
Yes.
Yeah, okay. So what are your second question? I'm sorry.
The second question is, can digital rock technology be a primary method, or should it just as a secondary approach to core analysis?
I love these questions. I love these questions. I would say, I hate to say, I mean, it really depends on what your objective is. I think sometimes this technology can be the primary technology. But I would say in order to understand, get a full picture, to understand the whole interval, I do see in most of the cases, we can use the more kind of full suite of kind of I would say fundamental understanding of the reservoir, like wireline logging, that more use our data as the calibration point for critical parameter to get the whole image of the information. So I do see, because again, so that is why let me just kind of explain a little bit more, see if I can somehow answer your question. When I got a permeability for each data point, but I cannot really kind of measure every point. We're pretty expensive, to be honest with you, because of the technology, because of the timing we spend for each sample. So for each well of, let's say, 100 meters of interval, we can do 50 meters of kind of 50 samples. But I got the results for those 50 or data points. So how can I create a continuous kind of profile of different parameters of the interval? I would love to use whatever kind of information you have, then use our technology more as an anchoring points. Then combine those two or more than two kind of technologies together to answer the questions you have. I mean, this is all about how much, no matter how good our technology is, it's more how much I can answer your question. So if I can use our technology incorporated with other data, would love to do that. It's not to show how good we are, is to how better we can get your questions answered. So I would say, again, to kind of answer your question, it will depend on the situation, but I don't want to say our technology will solve all the problem. I don't see that. Sorry, this might not be ideal answer, but I mean, I've been working. I don't want to kind of oversell our technology. I think we have been doing pretty good. We are the #1 kind of digital content analysis in China, so that is why we could go outside. But again, I do realize we cannot answer all the questions.
Okay, thank you, Mr. Dai.
Right. Yeah.
For Mr. Gigasakti, is there any further question?
Miss Puspitasari, excuse me, I would like to remind about the time limit. We only have 5 more minutes left.
Okay.
We still have 3 more questions from, I think the last question 3, Pak Rio, Pak Aldo, dan Pak Agus. Pak Rio first.
Yes, thank you, Mr. Sensen, for the very good presentations. I can understand that the data is take so much position. Yeah, as we know, the statistic play very well. You mentioned that we cannot rely on one data on the cutting. I can understand about it. What I want to ask is about CT scan technology is nowadays is quite popular, and also for virtual simulation. You show us the relative probability, which is, I think it's from visual simulation. Yeah, but it's not from the core, right?
Right.
My question is how much we can trust about the virtual simulation, like relative probability, since if we do in conventional core, we know detail like contact angle and etc. But when we use the virtual, maybe I don't know how much we can trust the data, because I think one of the advantages for the digital core is, yeah, maybe we can see the whole data, like you mentioned before, yeah, about the permeability, about the pattern, and etc. But for the virtual simulation, how much we can trust the data?
Okay, in the simulation, we use simulation for two things. One is get the permeability, another one is get the geomechanical properties, right? So that's a good question. So what basically, so several things we can do. When you have to, for each area, in order to buy kind of trust, we'll have to compare our results to the results people got more kind of, I would say, commercial or more industrially accepted technology. One example we did, or one of the questions, just give you one example. For permeability understanding, in conventional tile reservoir, people trust, in China at least, people trust NMR because nutrient density just not good enough. So people just NMR. Then what they do, okay, just compare your results with your NMR. That's the only way you convince people. Because I mean, you can explain how good your technology is, but at the end of the day, you have to compare the results with the people believe that the good technology. That's what we do. So more in detail, we just kind of try to define this. For some area, it took us a while to get the kind of reasonable results. So that's the lady kind of asked online, is to understand, and the chairman mentioned that question also. You will have to good understanding of the local geology, then to define your model to get a reasonable. So basically two things. One is to look at the model, to define your model. Another one is to show people your results can compare with another kind of results. We have done both.
Thank you, Mr. Dai. My name is Aldo. As you said, I just wondering, if I'm not wrong, we can build a reservoir rock model through your measurement porosity model, right? Am I right?
Yeah.
Yeah.
So I mean, the first one, I mean, how? Can you say it again?
Yeah. So we can build or conduct a reservoir model in field size.
Right.
Through your measurement porosity model. Core model.
Right.
Yeah. If I want to import your model to reservoir static software like Petrel or other kind, in what kind of type should we import your model? Format, the format.
Yeah. Let me try to see if I answer the question. Basically, my understanding is how we kind of define or build our model to calculate the geomechanical permeability results, right?
Yeah, can be a geomechanical
or
geological properties like permeability or porosity.
The second part. Well, the second part is how to kind of input or our data into another patch or software, right? For the simulation, I mean, I think I tried to answer that question already. I mean, we'll have to work with for each certain area. We read a lot of paper about that area. Try to use big data, and also use kind of more geological principle to define the parameter for the model. So we'll have to have a very good understanding of the local geology to get a good model. So the second part, I don't think that is, I mean, to import our data into another system. So for most of the time, should not be a challenge. Just look at what kind of data format another application used. But we do have, for most of the time, the kind of digital rock data is huge. We have to import most of the time, not the raw data, but the results of certain more the results of a product into a system, not the, it's very difficult to import the raw data. It's huge.
Okay. Can your model be imported as last?
Yes, we can create. Yeah, no problem. We can create last format.
Last format.
Results.
Okay,
Right.
okay.
No, that's not a problem.
Okay.
Thank you.
Thank you very much. Oh, the raw data is more like picture than the model.
Yeah, pictures. One is, well, there's several things. One is kind of digital, kind of last file. That's easy, and the image. I mean, if for image you can, there's always a way to get image into your system. Then for the raw data, it's very difficult. It's just too huge, and also people don't really know how to use it. So that is why we're based on your kind of objective to create what kind of data is useful for you and in which format. But technically, that's not a problem.
Okay, so we can request it there.
Yes.
Oh.
Yeah, we work together, look at what format you can accept, then create our data set in the format you can use. Okay.
Thank you, sir.
Thank you, Pak Dai. Good, impressive, and also very, very powerful for your insight. Personally, I would ask about I have some note here.
Okay, go ahead.
Can you implement digital rock for coal? Because by background, coal industries, coal commodity, that is only oil and gas. Could you implement this technology? Yeah. Firstly, secondly, when you are,
I'm sorry. Can we what?
Implement two coal commodities, right?
Okay.
Commodities, and also mineral commodities. Okay.
I love.
Yeah, that's right. That's right. Yes. A couple years ago, I have been work in this Gonyela mine and the Riverside mine, Australia.
Right.
Yeah, and also some collieries in Johannesburg. Yeah. Firstly, yeah. Secondly, I would ask about your data regarding with this statistical data. For your slide, gitu ya. You mentioned about the data, especially what's been porosity, right? Fracture showing to us about this Gaussian numbers. Yeah, Gaussian numbers based on your data. And secondly, in this your illustrate graphics, yeah, there's not only Gaussian numbers or this skewness based on your data. If you face with this some data that's not normal data, what do you do to revise or to correct this data? Yeah, in my understanding, we don't only interpret it from what's mean sea level on ground to some kilos. Right. Two questions. Thank you very much, Pak Dai.
So let me try. So first question, I don't think I have the answer, but we have been starting looking at if we can apply this technology to mineral industry, because now because of whatever reason the mineral industry is very critical. Now we started looking to apply our technology to that area. So that's still, I don't think I understood your second question very well. So can you say it again? Or was it your second question?
Go back your presentation. I will show to you. The
Okay,
data.
before we go, let me just use this example to answer your question. This is not the best example, but it can answer that question pretty much. So this is the cuttings. You look at the size, 1.5 micrometer. So the whole image is about 1 to 2 millimeter. So by looking at the image, I would say I feel pretty comfortable. This sample can represent the rock, because because we don't really see kind of any artificial or kind of engineering or kind of basically kind of any kind of fractures or other features created by drilling or kind of operations process. So for this kind of, we can, all these grains or minerals, they're pretty, we feel pretty comfortable it is in a kind of a similar situation when it is underground, right? So, but again, for this one also, but this is a pretty big piece. So we feel some fractures. There was a question if it's created by kind of processing, kind of artificial processing. But if you look at the whole picture, we feel pretty comfortable. Any measurements, any parameter we got from the sample can represent the rock. That's how I try to answer your question. I'm sorry, Justin. It's before. Again, I just love all those questions. I mean, which show you guys how much.
Which one, Pak?
Yeah, start this with that.
So move backward.
Yeah. That is. Yes. Yes, yeah.
Okay.
Yeah. Understood your data.
Okay.
Yeah. Almost we face with this our data, this Gaussian number or normal number, normal distribution. Yeah. The second data, what is the second data is skinless. Currently, or many problems we're facing with this uncertainty of our data.
Right.
Yes, but your data is good data here. Yeah, maybe you have insight for us over to make it look like this.
This is this data I took from my work back in the United States for Eagle 4. Okay, this is I don't know if you guys can understand what this. Thank you again. I'd love to share this slides. Okay, this is you guys all know the microseismic, right? So people use microseismic technology to listen or to measure the fracture events created by hydraulic fracking, right? So this is can represent the number of different kind of size of fractures created by fracking. So the big number so this is the Young's module. This is the number of events created by microchip fracture. What this slides really show is that, so for the lower Young's module, what you mean the rock is less brittle, less frackable, it's more soft, let me put this way. And onto this direction, the rock becomes strong. What this slides really show you, because people use, so I have one slide to try to explain the difference between brittleness and the frackability. So this is a good, perfect example. Normally, people say, well, the highest Young's module you have, the more brittle the rock will have. It is true. So if you move to this direction, the rock is very brittle, but why it has less fractures created? Because the Young's module is too high, the rock is too strong. I use granite and glass as an example to compare. What you mean, if you have a high Young's module, even your rock is very brittle, but still very difficult to create fractures because the rock is very strong. So this is the image I thank you for giving me the chance to explain the difference between Young's module, between the brittleness and frackability. the answer is your Young's module will have to in the middle area, which is not too soft, because it's too soft. It's kind of more kind of textural. It's very difficult to create a fracture. But if it's very brittle, but it's too strong, like a granite, it's very difficult to create a fracture because the rock is too hot. So this is how this image kind of I use this slides all the time to explain to people. You know, you cannot just use brittleness to design your completion. Sorry, I don't know if I kind of answered that question. But in terms of why the distribution like that, well, that's just the I'm happy it's a kind of normal distribution, but
if you want to, this is good for us, your insight. Related with this couple of months, last month, we faced with this fatality before. It's part of chaos soft material.
Right.
Yes. That's why I asked you.
Thank you.
You have any experience?
Well, yeah, the new again, I mean, this first time, hopefully I have, all great scientists. I so much appreciate it. So hopefully we have an opportunity to discuss more.
Okay, thank you, Mr. Dai, for the insightful presentation. But unfortunately, time limit everything. So that concludes our session. On behalf of organizing team, thank you to Dr. Dai Chunsen, IAGI, GEAR, CNLC, Asia Pacific, and ICOR Group, and PHSS, also all participants. Let's now take a group photo together.
Okay, thank you for the participation. For participant in Zoom, please turn on the camera. We are going to take a picture for documentation. Thank you.
Iya. Mbak Puspitasari bisa kontrol layarnya yang mau ditampilin apa?
Oke, bisa Pak. Paling itu saya minta tolong untuk head office zona 9 boleh stop share screen dulu.
Oh, stop share. Mana ya? Sorry. Ini ya. Stop share. Oke.
Oke.
Oh.
Baik. Untuk peserta Zoom diharapkan untuk menyalakan kameranya. Akan ditunggu sampai pukul 10:01. Terima kasih.
Mana ya?
Okay, let's moving
Hah?
forward. Okay.
Bukan. Disimpan filenya di mana sama si Mas ini? Wah. Mana ya? I cannot find the... Oh, bukan. Nah, ini aja. Hah? Nggak usah. Oh, ya udah.
Baik, kita akan melakukan dokumentasi, akan terdapat 2 slide. Oke, 1, 2, 3. Slide berikutnya, 1, 2,
Thank you
3.
for all participants. For the lunch is already prepared. Boleh diambil ya makan siangnya dari Bare Solok.
Oke, untuk partisipan yang ada di Zoom, sebelum meninggalkan ruang Zoom, mohon isi form feedback yang sudah ada di layar. Terima kasih. For participants in Zoom meetings, before you leave the meeting rooms, please fill this form to get the certificate. Thank you. Okay, this is the end of the virtual technical session today. Thank you for your participation. Please don't forget to fill this form to get the e-certificate. Thank you and have a nice day.